Hey guys, this is Saptashi here and welcome to our YouTube channel. Last few classes we are discussing about a technique called as regularization. And we have understood that there is something called as overfitting where the models try to actually memorize the data. Okay, and regularization is actually a shield against this tendency of the models to memorize. We have also understood that the more parameters a model has got, it is more prone to regularization. Okay, so neural networks, as they have more number of parameters, they are more prone to this problem of overfitting, and as a result we need to have specific discussions on regularization for neural networks. So here we have something called as a dropout, and this is a hands-on session. So we are doing in our regular Kaggle environment. The code is available as a Jupyter notebook, so you can download the code, you can edit it, you can run it and do whatever you want, right? So let's start by doing our regular housekeeping. Okay. Uh, so this actually we are also doing below over here, where we are also importing TensorFlow, Keras, and plot and this train test split that will be required, and then we are going to import the data set. Now let me tell you that we are using this Keras datasets function to load the Fashion MNIST dataset. Fashion MNIST dataset is an image dataset, okay, and it is a 10 class classification problem, very similar to our regular MNIST problem where there is handwritten digits. So this is also a 10 class classification problem. However, here we are dealing with fashion items, so that's why the name is Fashion MNIST. And it turns out that this data has more diversity, so is a more accepted test bed compared to the original MNIST. So let's just do that, and we are also using our validation set, right, which we have been using for early stopping. 20% of the training data we are keeping for validation, right? So we just want to see how our model deals with overfitting, right? We want to see that. Let's standardize the input. So we are going to standardize both the training, testing and validation set. Please understand, as this is as these are pixel values, intensity values, so it will have value between 0 to 255. So we can just standardize them dividing by 255. So you know that neural networks are highly affected by scale of the input, so it is advised to give it input between 0 to 1. So class labels are not included in the data, so we just need to add a class label. Okay, this is just for understanding or taking a look at the data set. And then what we are going to do is we are going to plot some of the observations. Okay, and we are going to produce a binary plot. So here you see the fashion items over here. So 10 items have been plotted with their corresponding labels. And as I said, that this is a binary image, right? So you see only black and white pixels. Now let us quickly look at the dropout strategy. Okay, so let's say that these are, so there are several layer of neurons, right? And the input from the previous layer goes to the next layer. However, when the outputs are going, what we do is we apply a probability called as keep probability. And for some cases, the nodes actually doesn't participate in training. Okay, so maybe the first iteration, okay, these three neurons are participating. Next iteration, these three neurons are participating, and as the probability is 50%, roughly half of the neurons always participate. Okay, and that's how you complete the training. So you go from iteration to iteration. Every iteration you are kind of training a different architecture because different nodes are participating. Okay, and then finally you when you evaluate, you actually use all the units, right? Because now all the nodes has got some weights or other. So for evaluation you use all the nodes. So let's understand, or let's revisit the characteristics quickly. So it's a very simple regularization technique, all right? And you associate a probability. The probability, if you associate probability of 50%, then 50% of them will participate, and as they are participating probabilistically, the network cannot be overfit, because overfitting means that particular node, so all the nodes will try to get a lot of weight, a lot of priority. Okay, as the weights go up, the nodes may be overfitting. Okay, And if you do not allow all nodes to participate in all that training, so they cannot actually try to maximize their weights, right? So this is how you try to prevent it from overfitting. And another very nice interpretation is that you can think it as an ensemble model, because different iterations, there are different models that are participating in the training. And when actually you are doing an evaluation, there the models weights are averaged out, right? So that's what happens in ensemble, right? So you train different models, and then you finally average out the prediction. Okay. And now let's look at the model creation. So we are not going to use it, like we are not going to run it, because it is going to take some time. So it's a very simple base model that we are creating. So we have, this is a sequential model. The input shape is 28 into 28, because it is a 2828 binary image, or 2828 image. So we are just flattening it. Then we have a dense layer. So this is a hidden layer of 300 nodes, and then you have a softmax layer. Why softmax? Because it's a multi-class classification problem. And when you are going for dropout, so we are going to compare base model with the dropout model. Only thing that we are going to do is we are adding a dropout layer. So dropout is actually a layer, you see. Okay, and we could have added, so after every layer we can add a dropout. So we could have added a dropout even after the hidden layer. Okay, all right. So next what we do is we compile the model, and when we are compiling, the main important thing is what kind of loss function that we are going to use. So we have discussed about loss functions in great detail. So if it is a classification problem, it is a cross entropy is the best thing. Okay, if there are two classes, it is binary cross entropy. As you have 10 classes, it is categorical cross entropy. And the class labels are available like 1 2 3 4 5 6 7 8 9, like that way. Okay, so that's why it is called sparse. And if you have used like if you have used in a one hot encoding format, so every label would have been a 10-bit binary string, and if it is the 8th class, then on the 8th bit will be on. So if it is like that, you use categorical cross entropy. And we have seen that Adam optimizer is a good optimizer, and metrics we are just going to look at accuracy. Okay, all right. So we have already run this, because that otherwise it would have taken some time. So there is no big difference on what we are doing in the model fit. And what let's concentrate on how the accuracy graph looks like. Okay, let's just concentrate on this. So this is where we have not used any regularization. So you see that the training set accuracy has actually continuously has gone up, right? So it is going at a level like 0.97 or 98 steadily. And this is your validation set accuracy, which probably is telling that you have saturated already around maybe 10th or 15th iteration. Okay, all right. So now let's again look at the performance of this model. Okay, so let me run this on the test set, right? So we are getting an accuracy of 89%. Okay, and now this is how we fit the model with dropout. So again, there is no difference, but this is with the only change is that this is model 2, because model 2 we added the dropout layer. Okay, and we have similar epochs, but then again it is better understood with this graph where we are plotting epoch wise the training set accuracy and the validation set accuracy. Okay, and you see over here, so one big difference that you see over here is that the training set has not, the training accuracy has not gone up to 0.9. So this is what we were trying to do, right? That it is not overlearning from the training data. Okay, and maybe not always you will get a better accuracy using overfitting. So like in this case, okay, you will get an accuracy of 88.79%, which is little less than 89%, right? But on different iterations, you will see that this model will evolve as a more robust model. Okay, and this is one of again very simple techniques of regularizations. Okay, so thanks guys for watching our video, and I will encourage that you please run these codes. Once you run, your concepts will be much more clear. Okay, and then put your queries, do what, look at all parameters, whatever parameters it is, accepting, state, test with different type of probabilities, and share your results with us. Thanks so much guys for watching this video. Please like, comment and subscribe. Thanks once again.